Good morning, everyone. So this is the first example for the fins. So we have a stainless steel spoon. This is an introductory example. Therefore, we are trying to understand the concept. Then we will have the real world example. So we have a stainless steel spoon inside the water, and the water is 100 degrees Celsius. It is given here that boils, and the temperature is 100 degrees Celsius. And the room temperature is 25 degrees Celsius. This is inside a room where the temperature is 25 degrees Celsius. And the cross-sectional area of the handle of the spoon is 2 by 30 millimeters. So this is the cross-section of the spoon, and we can approximate this one as a rectangle. Okay, so if you approximate this one as a rectangle, you will have 2 millimeters into 30 millimeters. Okay. And then it extends 180 millimeters in the air from the free surface of the water. And from that part to this free surface of the water, this is the free surface of the water, you have 180 millimeters. If the convective heat transfer coefficient is 20, so the convective heat transfer inside the room is 20 watts by meter square Kelvin. This is actually combined heat transfer coefficient. It combines radiation and the convection together. Determine the temperature difference across the exposed surface of the spoon handle. So it says that find the temperature difference here and at that point. Between these 2 points, what's the temperature difference? And the list approximations, we will list approximations and take the thermal conductivity as 15. Thermal conductivity of the stainless spoon is, let's write here also, it is 15 watts by meter square Kelvin. So K spoon is 15 watts by meters Kelvin. Okay, this is the example. First, we should start with our approximations, and then we will do the example. The approximations are the famous fin approximations. The one is that if this one is the spoon, let's assume that this one is a rectangular spoon. First approximation that we are saying is that the heat transfer occurs in only one direction. So this part is hot, 100 degrees Celsius, okay, and this part is cold. And we are assuming that heat leaves the spoon in only one direction, this part. This is the direction that heat leaves the spoon, okay? Only in one direction. So there is no heat transfer in this direction. This part is ignored. Why? Because the thickness of the spoon is very small, okay? The thickness small, okay? If it is very small, there cannot be any transverse heat conduction. This is the first approximation. First approximation is that 1D Q. And the second approximation is that the K, the conductivity of the material, is isotropic. K is isotropic. Isotropic means that, for example, if this is your spoon, okay, and at this point you have some fixed K value. If you go another direction, you have the same K value. If you go another direction, you have the same K value. In other words, K is independent of the direction. We can say that the material is perfectly homogeneous, or atomic structure doesn't affect the value of the K in any direction. And the third one is that H is constant. So we have H inside the room, and we say that H around this spoon is constant. Okay, these are the famous approximations that we are using for fins. The first one is the 1D, and the K is isotropic, and the H value is constant. Okay. By using these approximations, now we can start to solve our problem. Firstly, we should find what type of the fin is this spoon. What type of fin can we assume? So we know that, firstly, let's go to the table. So we have different boundary conditions, okay? So these are the tip boundary conditions for the fins. And these are the base, which is the same for all of the fins. And the tip boundary condition, the first one is that, so infinitely long fin. So L tends to infinity. For the spoon, this cannot be true because spoon has finite length. On the other hand, this part of the spoon is not always at room temperature, because most of the time we cannot touch the spoon. It means that the spoon has a different temperature than the room. Therefore, first option is not true for our case. And the second option is that the temperature at the tip is given. Tip is given. If you look at the question, the temperature at the tip, this part, is not given. Okay, there is no value for this one. Therefore, the second also is not true for our case. Now we have come to the third approximation and the fourth approximation. And this one says that the tip is adiabatic, and this one is at the tip CV is same as CD. And this one is more realistic approach for the spoon, and this one is for making things easier. Okay, we will first do example as a convective tip. We will say that the tip is convective, and then we will use the adiabatic tip approximation, and then you will see the error in our case. But you should understand that convective tip is the most realistic one. Why do we use adiabatic tip? Because adiabatic tip gives easier calculations. You can see this part is easier, and this part is easy, and these parts are complex. Therefore, we are trying to assume that it is adiabatic. But adiabatic assumption is also realistic. Why it is realistic? Because the thickness of the tip, this thickness of tip, it is very small. It's very small. As it is very small, and it doesn't have any E exposed for heat transfer. Okay, very small. Exposed area for heat transfer is very small, and therefore we are saying that since this area is very small and there cannot be any heat transfer at the tip, and therefore we are assuming that the tip as if it is insulated or it is adiabatic tip. Okay, this is only for, so I should write it here, adiabatic tip only for easy calculation. Okay, in real life there is no adiabatic tip. Okay, this is very important. In real life you will always have this CV/CD approximation. Firstly, I will use this CV/CD approximation and this CV/CD approach and solve the problem, and then I will use adiabatic approach, and you will see that there is no large error between these two. Okay, let's start to solve the problem. For solving the problem, we should have the m value, which is HP by KAC, and we should have this theta by theta base. Okay, we should solve it, and I will solve the problem in Excel. Okay, go back to Excel, and I will write the values that are given in the question. Okay, first value is, so the base temperature is 100 degrees Celsius. The base temperature, I mean this part. Okay, this part is 100 degrees Celsius, and then as you go along the thickness, along the length of the spoon, the temperature drops. Okay, so let's write it. T base, it is 100 degrees Celsius. Make it larger. Okay, good. And then room temperature, T infinity, is 25 degrees Celsius. Then you will have the tip cross-sectional value, so we will write thickness is 2 millimeters, and then you have width is 30 millimeters, and the length is 180 millimeters. So I should convert this one into SI units. So first, the 2e minus 3, it means that meters minus 3 is again meters. So 180e minus 3, 10 to the power of 3, it makes again SI unit. And then convective heat transfer coefficient is 20. And then determine the temperature difference, and then conductivity is 15. Okay, these are the values that we have. Now first let's use the convective tip as we have said. First we should write the formula. I will write the formula first upstairs and then downstairs and then divide, because if you write all of the formula at the same time, it will be very confusing. So first I will write downstairs, upstairs, CV. I should note this CV. For upstairs of the CV, I will need m value, therefore I will need insert for m value. M value I will need HP KAC, therefore I should calculate perimeter also here, so perimeter. And I should also calculate a cross-sectional area, therefore insert again AC. cross-sectional area. So first the perimeter. When we mean the perimeter, we mean the, look at the cross-section of the spoon. Let me open another slide. So this is the spoon. Just 3D. 3D. This is spoon that we have zoomed. It is rectangular. So when we say the perimeter P, this is the perimeter of this cross-sectional area. So you see this perimeter. Okay. For uniform areas across the cross-section, and also you should note that this table is only for uniform areas. Okay, very areas will not change. In our case, area doesn't change, therefore we will use this P, and then you will have the AC. AC is again this cross-sectional area. And we should note these two. So first the AC is this cross-sectional area, and the perimeter is again this cross-sectional perimeter. Okay, let's calculate it, and we have said that this part is 2 millimeters, and this part is 13 millimeters, and this length is 180 millimeters. Okay, so the perimeter in our case will be, so 2 plus 13 into 2, because there are 2 of them. And the cross-sectional area will be 2 into 13. These are all millimeters. I will convert it into meters, so no problem. Okay, let's solve it now. Let's go back to here. So it will be 2 times width plus the thickness. The cross-section area will be thickness into the width. So the M value will be, if you go back to formula, HB by KAC. So if you go back to formula, so it is square root of HB by KAC. That I will take square root of H into perimeter divided by K into AC. Okay, so I have got this M value, and then I will calculate the upstairs of the formula. The upstairs of the formula is cosh ML minus X. So you see there is a variable X. Variable X here means that, so if you go back to this teaspoon, the variable X means that, so this is the base. So I should use different color. This one is the base, T base. Okay, I can find the temperature here. I can find the temperature here, temperature here. At any point, I can find the temperature. So the X direction is this one. Okay, so if I say that X is L, then I will find the temperature at the tip. It means that it is tip. Therefore, I will enter a variable X coordinate to calculate upstairs of the formula. So it will be X coordinate. And for this case, I'm saying that X coordinate is 180 millimeters, which is the tip of the fin. But for the, I can make it variable. It doesn't matter. So let's go back to our formula. So it will be cosh ML minus X. It will be cosh M minus M times L minus X. So this is our length, and this one minus X. And then plus H divided by, sorry, I should take this, H divided by M into K. M into K. And multiplied with cosh, again, this one is shine, again ML minus X. So it is the same here. Okay. This one, actually you can you see from the formula, this is shine, so L minus X is 0, that's why this part is 0, and the L minus 1 is 0, L is 0, M into 0 is 0, therefore cosh is 1, therefore this upstairs makes 1. Now let's count the downstairs. The downstairs of the CV formula, I will use this one, cosh M into L, M into L plus, so again this H by MK, so H divided by, in the brackets, M into K multiplied with shine into M into L, M into L. See, this one is 602. So let's calculate the formula. The formula will be CV theta. Theta CV, it will be upstairs by downstairs. Okay, so let's make sure the values are correct. So this one is, so cosh, so m into L, J2 is m into L, which is E2, that's right, plus F2 divided by F is H, yes, m into K, so again J2 into K, which is G2 into shine into J2 into E2, shine into, so these are correct, okay, no problem. So we have finished the theta CV formula. Now let's calculate the temperature, and this formula is theta divided by theta base. So what we are doing here is that, so we have the formula here, which is theta divided by theta base, and which is the formula that I have calculated. So theta is T minus T base, and this one is T base minus T infinity. So then this one is infinity, sorry, this one is infinity. So I will have T is equal to T base minus T infinity multiplied with the formula that I have calculated in Excel plus the infinity temperature. So I will do this stuff in Excel now. Okay. So you will have, so I'm calculating here, so T by CV. Okay, this is result of the CV calculation. I will do the same thing for adiabatic tip and then see the difference. This CV will be T at the base minus T at infinity times the temperature that we have here plus the infinity temperature, T infinity. See, this almost 25 degrees, and but now we'll approximate this one as the adiabatic tip. Okay, let's go back to this one. So we'll calculate it as adiabatic tip. The adiabatic tip formula is cosh ml minus x divided by cosh m into L. So let's do it. So firstly, I should calculate this one is easier, therefore I will do all of the formula together. So theta, so let's use another theta of adiabatic. So you will have now, so cosh again m into L minus x, m into L minus this x divided by the downstairs, which is cosh into m into L downstairs. Press it, I've got this value, and this is again the formula that I have calculated. If you do the similar approach here, so I should multiply the difference in temperature plus the T infinity temperature. So it will be that TCV, no, it is adiabatic. T adiabatic will be equal to, again, T base minus T infinity multiplied with this formula plus the infinity temperature. See, it is 25.12, it is 25.12. You see the value? The values are very close to each other. So the thing here is that the thickness of the spoon is 2 millimeters. Okay, so this affects the result that, so it says that the cross-sectional area at the tip is very small, therefore you don't have any temperature change. Let's increase the thickness of the spoon and let's see how it affects the dimensions. Let's make it 4 millimeters. And then you have a larger, the error decreases a bit more, so let's make it 5 millimeters. Okay, 8 millimeters. Okay. You see they are in accordance with each other, so that the error is not too much. It is 0.13 degrees Celsius. Okay, and the width also is very small, so you can play with these numbers, and you see that after some step you will see that the value error becomes larger and larger. Now it is 1 degree Celsius. We are approaching 1 degree Celsius. Okay, and then let's correct the dimensions. Thickness is 3 millimeters and the width is You see the error is too much small. So what we can do now is that, so therefore, if this thickness, the width ratio, if these are very small, we can approximate it as adiabatic tip. But another thing here is that you can do, to be accurate in your calculations, you can calculate the ratio, which is called so to be sure that your tip is adiabatic and you are close to adiabatic calculations, what you can do is that you can calculate the ratio, which is called the tip area to exposed fin ratio. So it is called AR tip. So it is the ratio of the tip cross-sectional area divided by the area of the exposed of fin to convection. Okay, if you calculate this ratio, if it is very, very small, and then we can approximate this one as adiabatic tip. Okay, let's calculate this one and let's see if our calculations are good. So area tip, we have calculated it. Now let's calculate the exposed fin area. So we have calculated this one. This is in Excel. And now we will calculate the exposed area of the fin. So in this exposed fin, you don't include the tip area. For exposed area, you have 180 millimeters into this thickness. You have two of them. Let's calculate it. Area S fin. It will be 180. Or you can multiply the perimeters. It will be easier. Multiplied with 2 times this one plus that one. It will be 2 plus 13. And you will get the surface area. It is perimeter. This one is the perimeter. And this one is the length. So P into L, you will get the exposed surface area. Or you can calculate one by one. So you have one surface here, 180 into this thickness. You have another surface here, again 180 into this thickness. Again back on the left surfaces. Okay, if we calculate this exposed ratio and find AR tip, and if it is very small, then we can say that it is good for adiabatic calculations. This is another approach to be sure that your calculations are okay. So AR tip. It will be first I should calculate AS of the spoon and then AR tip. AS of the spoon will be the perimeter into the length. So I have calculated the perimeter and then I multiply with the length and I have got this value and then I divide the tip area, which is AC, which is the same as the tip because it's uniform area, divided by spoon. And you see the value is 0.004. Okay? Therefore, you can approximate this one as the adiabatic tip and there is no any error. So that is good for the first part. And the next part is that you can say, we can use corrected length to decrease our error. Okay, so here we have some error. So to decrease that error, we can use the corrected length. Let's use that one and to see how our error changes. Okay, now I will use the corrected length. Okay, so the corrected length is, if you remember, so we have in a surface, fin surface, that this part is exposed to this by the CD, CV, boundary condition at the tip. But most of the time, we can convert it in the adiabatic tip by adding this ratio. So if we add this ratio to the tip, and then this converts into corrected length because we have a length here, we have another length added, and this two length is called the corrected length. Okay, so if you use this corrected length, then you will see that this error decreases more because by using corrected length, we are moving from the convective tip to adiabatic tip. Okay, as we have said, adiabatic tip is easier to calculate, and therefore we are using these manipulations. Okay, so let's calculate the AC of the tip by PT and find the corrected length. So let's go back to we have LC. So it will be the original length plus we'll have the cross-sectional area divided by perimeter. This one is the corrected length. So now you will do all of your calculations with this corrected length. Okay, so we are assuming that the actual length is this one. Okay, therefore you should add here x corrected coordinate, because this coordinate ends at 180, but in this coordinate you will use more than that one. Okay. So we will use the same formula for the adiabatic calculations. So where is the adiabatic? So we have this formula. I will copy formula here. So first let's assume that so we are here calculating the tip, therefore they are the same. So now theta adiabatic, but now it is corrected. Correct. Let's calculate it. So we have the same formula here. I will copy paste same formula and then correct the value. So here you see the E2, which is the original length. Now I should use the corrected length, which is I2. At I2 it is here, so I7. So again here you have the E2, which is the original length. I will use this corrected length. So, okay, everything is okay. You have the J2, and we have, let's check it, K2, which is x coordinate. Yes, okay, I should convert it into also this x coordinate, and also if I don't have any J2, again is M. There's no problem with M. H perimeter by KAC. Okay, let's calculate it. So this is the theta adiabatic corrected. So let's calculate the T adiabatic. T adiabatic, this is the same formula that I will use, but changing only the values. So it will be A2 minus B2, that are the same, into D7. Instead of D7, I will use this formula, which is K7, and the plus B2. B2 is the temperature here. Let's calculate it. It is 25.15. You see, the values are very close to convected tip. Okay, so you have increased your, let's say, accuracy one more degree. Okay, so now it was 128. So the original one is, the accurate one is 125. So you are very close to 125. You can, so by this way, you can increase your accuracy of the calculations by using corrected length. Okay. It's not too much, but at the end, it is accurate. Okay, so by the way, you can change the x value here. So let's make it as variable. So for example, 0.1, 100 millimeters. So we are trying to find what is the temperature at 100 millimeters. It is 26.5, or you can find the temperatures at 80 millimeters. 8 millimeters. 59. We can also draw the graph of it. So let's make it corrected as here. It will be same as this one. So you can plot the graph of the temperature versus x. Okay, so let's plot it. Temperature versus x plot. I'll finish this part. And now let's plot the graph, how the temperature changes across the spoon. So what we are saying is that, so we have the spoon here. One is rectangular, one is also rectangular. So we are trying to understand what is the temperature change across the spoon. So here we have 100 degrees Celsius, and what is the temperature at each location. So it will be exponential, but plot its graph. Okay, so now let's do it. Okay, so now let's plot the graph of the temperature across the spoon. So as I have said, the temperature change along the direction of the spoon. So what we will do, we will change these x values and try to find the new temperature values for that changed x value. So what will I do that? I will copy this part into here. So we have the temperature values, but I will make one more here, one more here, one more here. How many rows do we have now? 7 rows we have here now. So I will change the values of the x. I will first start from the 10 millimeters. Let's say 0 millimeter, 0, 10, 3, and then I will plot it at 20 millimeters. Increase at 20 millimeters, temperature value 40 millimeters, 60, 80, 100, and 120. I will do the same thing for this one. This one is calculating the temperature value for 0 millimeters. So one more row, it calculates at 20 millimeters and the 40 millimeters and the 60, 80, 100, and 120. Okay. Similarly, I will do the same calculation for adiabatic tip temperature. So I increase these values, but I first increase this theta adiabatic because this calculates with respect to that one. So again, EAS of the spoon is constant, so I can make it as, now let's calculate the theta adiabatic, T adiabatic with corrected length. So I should increase these values too, but first let's plot this TC. And now let's calculate the adiabatic temperature across along the spoon. So firstly I increase the number of rows. All of them shows 25. First increase this one. So because this one calculates the temperature with respect to theta adiabatic, therefore I should change the parameters here so that we have reasonable parameters here. So next is this one is corrected. Let's correct it. The tip assumption. So increase it. Again, I should increase this part. And also related to that one. So I do the same thing. 0, 2, 4, 6, 1, 8. I have the same values, and the corrected length is constant, and the tip ratio is, so we don't need that formula. The AS is constant. So these are the adiabatic tip corrected, these are the adiabatic real, and these are the CV. If I plot it and to see how the values change and what are the errors, so we will insert chart here, then scatter. I will use this one. Is better. This one is better. I will use the scatter, and I will erase all of the data. Okay, so I will add the first data. This one is the convection. Convective tip. Okay. The x values are, these are the x values. Use the chart. Okay, so till 8. These are the x values, and the y values are the temperature values here. See how our graph looks like. So our y values again. These are the y values. So these are x values, these are y values. Let's see it. Yes, this is the shape of the convective tip. Now let's add one more graph here, which is that adiabatic tip. Adiabatic tip. Now let's add it. Again, the series name, this one is adiabatic, and then the x values are the values here till 8, so row 8, and then we have the y values, which is the adiabatic. Edit, and this one is okay. Now let's add one more. So first let's see how our graph looks like. You see the values are coinciding at each point. Okay, so it is very good approximation. Change the size of the markers so that you can see it. So the marker, so let's use a different one. This one is okay. Okay, the rest is no problem. So you see all of the values are coinciding. So now we add the adiabatic corrective. You will see this one also coincides the values that we have here. So let's select data, add this one is corrected, and x values will be values that we have here. The y values will be correct. Okay, you can add it. Okay, so all of them are in. So let's again change it to this one. Okay, good. This, so all of the values are coinciding, so therefore you don't have lots of error here. So this is exponential, and you can find the trend line for this one. So you can add the trend line here, and the trend line we should select exponential. The exponential trend line is okay for us. Okay, display equation on chart. You can see the equation is this one for the exponential graph.